we spent time looking at boundary equilibrium bifurcations. Boundary equilibrium bifurcations, so we're back thinking about ODEs now. Sigma. So we've got a piecewise smooth system of ODEs and some switching manifold sigma. And the idea is we've got some regular equilibrium, and as we vary the parameters, the equilibrium collides with the switching manifold. So that's what we call a boundary equilibrium bifurcation. And so far we've just looked at equilibria associated with these. And so what we've found is that there's only one regular equilibrium and there's one pseudo-equilibrium. So a pseudo-equilibrium is an equilibrium of the sliding vector field. And generically, these are the only two equilibria you can have. And we saw that there are two cases. First, there was persistence. So what happens is the regular equilibrium collides with the switch manifold and turns into a pseudo-equilibrium. And then the second case was a non-smooth fold, where these two equilibria coexist, and then they collide and annihilate at the boundary equilibrium bifurcation. However, there can be other invariant sets created at a boundary equilibrium bifurcation. You can have limit cycles, chaotic attractors, pretty much anything. So that's what I'll start talking about today. And then later today, we'll start looking at continuous systems. Okay, so to start with today, I wanted to show you an example. So we're going to consider the Gause predator-prey model, which originates from a wonderful 1936 paper by some Russians. And okay, I don't have the equations. Where are the equations? Oh, there they are. Okay. Let me describe this first. So basically, it's a predator-prey system. In this case, the predator is a single-celled organism, Paramecium bersaria, and the prey is yeast. And so here's the data from a series of experiments. And so for each experiment that they measured the predator population and the prey population, and they drew a black dot for the initial state of the system, and then they measured the populations at later times, and so they drew some circles, and then they connected them up with curves that they drew in by hand, and put some arrows on to sort of indicate the evolution of time. And so this effectively gives them a phase portrait of the two-dimensional dynamics. And this is all just experimental data. Okay, so then they constructed a mathematical model. It's a predator-prey system, and their model is based on the assumption that when the population, or when the yeast population, when the yeast population is below some threshold, then the yeast forms a sediment, and it cannot be consumed by the organisms. So in their model, they've got this discontinuity to where RC is the threshold value of the yeast. So R would be R is the prey, the yeast, and C is the predator, the organism. Okay, and so then here they've simulated their model, except you have to remember this is 1936. So they don't have MATLAB. They've just sketched orbits by hand. So here's they've sketched. But what I think is really interesting is that this predates Filipov. So they don't have any mathematical formulation for sliding motion. But nevertheless, they've decided that somehow orbits should sort of slide along the switching manifold based on some arguments regarding smoothing the system. Um, I think that's really fascinating to find this very old paper showing sliding motion. More recently, this is a 2011 paper that their model was described in sort of a more modern mathematical framework. And among other things, we have a boundary equilibrium bifurcation. So here are two-phase portraits of their model, either side of a boundary equilibrium bifurcation. So the switching manifold is this vertical line. Just ignore the nearly horizontal one. Ignore this one, that's a null line. So the switching manifold's here, and this dot is a pseudo-equilibrium. And then they vary parameters, have a boundary equilibrium bifurcation, and now you've got a regular equilibrium. It's an unstable focus, and surrounding the unstable focus is a stable limit cycle. I think we could see that back in here. You've got a stable limit cycle. So it's a stable pseudo-equilibrium changes into an unstable focus. It's a case of persistence, but you also get a limit cycle being created at the same time. Okay, so enough on that. Right, so yesterday we looked at the normal form for boundary equilibrium bifurcations. And so let me describe the normal form in 2 dimensions. So I'm going to use some different names for my parameters. So here's the matrix A, and yesterday the numbers in the first column, those numbers were minus A1, minus A2, and so on. But here I'm going to call them tau L and minus delta L. But because tau L is just the trace of this matrix, sorry, it's the matrix C because it's in normal form. That was my notation yesterday. And delta L is the determinant of C. So these are convenient names for our parameters because they have some nice, straight meanings. And then this vector, this was the vector D, where we had D1, D2, and so on. And remember, in our normal form, D1 is either plus or minus 1. So for today, we'll assume that D1 is minus 1, which means that orbits are approaching the switching manifold from the right. If you want to understand the case D1 is positive 1, you can just reverse time. Okay, so we've got 3 parameters, tau, delta, and D2, as well as the border collision bifurcation, as well as the boundary equilibrium bifurcation parameter mu. Okay, so first we'll consider what happens when mu equals 0. So with mu equals 0, we've got an equilibrium on the switching manifold. Sigma. So we have a boundary equilibrium, a boundary equilibrium, and it turns out there are 8 cases you can have. So this was done by Filipov in his 1988 book. So ignoring special cases like that the parameter D2, for example, is 0. Ignoring special cases, if you're just looking at generic scenarios that are topologically distinct, there are 8 cases. So the left-hand column has D2 negative, sliding motion is towards the origin. In the right-hand column, D2 is positive, sliding motion is away from the origin. In the top, we've got that the regular equilibrium is a saddle, then it's a stable node, an unstable node, and lastly, the regular equilibrium is a focus. Okay, so this is all just mu equals 0. So as we vary the value of mu from 0, we unfold the bifurcation. At least that's the word we like to use. So let me take this bottom left case as an example, and I'll draw some phase portraits on the board for values of mu not 0. So for mu not 0, we choose the appropriate sign of mu so that the regular equilibrium is admissible. It's a focus, and really there are two cases. Either the focus is stable or unstable. So if the focus is stable, orbits go in. And in this case, sliding motion is going downwards. So here's what the phase portrait would look like, but with the focus being stable. Alternatively, the focus could be unstable. That's spiraling out. It spirals out, but it's going to reach the attracting sliding region, slide downwards. And so in this case, we'll get a stable limit cycle. So there's our stable limit cycle. And so this is exactly the case we have in the Gauss predator-prey model. Okay, so this particular case has two different unfoldings, and I've given you numbers for all the others. Some of them have just one unfolding, some have more. But this was done in a very nice paper by Kuznetsov, Rinaldi, and Greg Nanny, 2003, and they found 10 different unfoldings. Unfortunately, they missed 2, and this was mentioned by Paul this morning. You just have to just very carefully make sure you're not missing any of the cases. And this was done 2016 by a group at Bristol. That they found that the Kuznetsov paper missed 2 of the boundary equilibrium bifurcations. So really there are 12. And here are the 2 that they missed. You have a stable node and a saddle pseudo-equilibrium, glide and annihilate in a non-smooth fold. And they also missed this case, which I think is quite interesting. So here you've got a repelling node, and despite the fact that the system on the left is completely repelling, you're able to get a stable pseudo-equilibrium. Okay, so 12 cases for boundary equilibrium bifurcations in 2 dimensions. In 3 dimensions, okay, so here's our normal form again, and again I've come up with new names for my parameters. So instead of minus A1, minus A2, minus A3, I've got these labels, which I think are more convenient. So why do I think that? Well, first of all, tau is the trace of the matrix, which means it's the sum of the eigenvalues. Tau L is so that the matrix has 3 eigenvalues counting algebraic multiplicity. So let's call them lambda 1, lambda 2, lambda 3. Tau is that. And then delta L is the determinant of the matrix. That's the product of eigenvalues. And then in this 3 by 3 case, we need a third parameter. That's sigma L is what's called the second trace. And let me write the formula for it in terms of the eigenvalues. Plus lambda 1, lambda 3, plus lambda 2. You could possibly imagine how this works in higher dimensions. You're just adding up all products of certain lengths of the eigenvalues. Okay. And then I've also got new names for my parameters in the vector D. So again, I'll assume D1 is -1. So here are my parameters D2 and D3. But we saw last time when we write down the sliding vector field or the normal form, then we get this nice companion matrix in the normal form. And so instead of D2 and we get minus D2 and minus D3 here. So we might as well call them tau S and delta S, because those are the trace and determinant of this matrix. So I think these are nice names for the parameters. So now we've got 5 parameters in addition to mu. And we could think about different cases. Unfortunately, there's far too many cases to consider. The system can be extremely complicated. There's no hope of classifying all possible dynamics. So let me just show one example. So here's a phase portrait of 3-dimensional boundary equilibrium bifurcation normal form. So I've chosen parameters so that the regular equilibrium is a saddle focus. So it's got a 1-dimensional unstable manifold, and it's got a 2-dimensional stable manifold with complex eigenvalues. And the pseudo-equilibrium is a focus. It's an unstable focus. And you could do the analysis yesterday to show that with that you have to have non-smooth fold. A question? Yeah, so the idea is of a normal form. It's a simple system for a particular type of bifurcation. So I mentioned yesterday very briefly the normal form for the saddle node bifurcation. It's some particular equation. And then what I've shown you is the normal form for boundary equilibrium bifurcations. It's another type of system. And so each type of bifurcation could or should have some sort of normal form. If you have, so any physical system, you have your particular ODEs. Maybe you've got some 4-dimensional model of something that you're interested in. If you have a boundary equilibrium bifurcation, as long as it occurs in a nice generic way, so nothing funny is going on, then in theory, you must be able to do a coordinate change to put it in the normal form. That's the purpose of the normal form. I suppose when you're getting into sort of global bifurcations, things get more complicated. But for local bifurcations such as these, you're just looking at the first few terms in some series expansion. Yep. Okay. So in this particular case, we've got corresponds to a non-smooth fold. So you've got two equilibria collide and annihilate. But we also have some more dynamics going on. The dashed the dashed loop, that is a stable periodic orbit. And then I've also got what appears to be a chaotic attractor. So I've got two coexisting attractors, a seemingly chaotic one and a periodic one, as well as my two equilibria. So at the boundary equilibrium bifurcation, all of these invariant sets sort of collide and annihilate. Yeah. Okay, so to understand what's going on here a bit more, we could construct a Poincare map. And this map is going to be one-dimensional, which is rather helpful. So orbits are going to slide on the switching manifold, and orbits peel off from the switching manifold where there's a fold. Remember? A lot of the systems we've looked at have been two-dimensional, so folds have been points. This is a three-dimensional system, so that there's a curve of folds. It's actually a line, because the normal form makes it as nice as possible. So whenever an orbit peels off from the switching manifold, it has to do so on this line. And so I can construct a return map on this line. So for any point on this line, I look at where it next hits the line, and that's how I define my return map or Poincare map. And here's what the map looks like. It's kind of wiggly, and by putting in the 45-degree line, we can see we get a stable fixed point, so that corresponds to the stable periodic orbit. And well, we get some kind of this part of the map is unimodal, and from our experiences with the logistic map and quadratic maps and so on, it's sort of not surprising that we would get a chaotic attractor in there. You'll notice it's a smooth map. So we have our piecewise smooth system. We've done a Poincare map, and the map is smooth. You'll also notice this wiggling going on. And so at this point corresponds to where, to down here, to the point where I would go into the regular equilibrium. And so I've chosen my parameters very near a Shilnikov homoclinic orbit. So a Shilnikov homoclinic orbit would be and a homoclinic orbit to this point. So you have the unstable manifold goes out, and then it returns back in there. And from the smooth theory developed in the 60s by Shilnikov, established all sorts of nice results regarding chaos associated with Shilnikov homoclinic orbit. Okay, so I think that's enough on that example. If you want to learn more about that sort of thing, nice paper by Paul quite recently, Shilnikov chaos, boundary equilibrium bifurcations. Okay, so what we're going to do now is move on to continuous systems. Okay, so here's the sort of system we've been looking at, but now we're going to assume that the system is continuous on the switching manifold. So if I evaluate FL and FR, at some point where H of X is 0, then I have to get the same thing. Right, so we're going to study boundary equilibrium bifurcations. So just with the same kind of setup that we had yesterday, but we're going to assume that the bifurcation occurs at the origin when mu equals 0. So the switching manifold passes through the origin. The normal vector, call it zeta, that has to be non-zero. And we've got a equilibrium at the origin when mu equals 0. Okay, and so just as we had yesterday. So that enables us to write. How did I do that? Went to the end. Okay, so as we had yesterday, that enables us to write FL like this. L of X. Oh, it's mu as well. Okay, so that's all the same, but now we get something different for FR. So previously, we had no assumptions. It was a discontinuous system, so FR was just some vector, little c. But now we need to use the continuity assumption. So let me explain where this comes from. It's going to take me a few lines on the board. So first of all, it's continuous at the origin when mu equals 0. So there's no constant term. So there'll be a linear term with x. So there'll be some matrix times x, and again there'll be some vector times mu. And so first of all, by continuity, this vector has to be the same as this one. And the reason for that, just put x being the 0 vector. You get b mu has to equal this thing. So therefore, this has to be the vector b, same as that one. Okay, so that's all well and good. So the more interesting thing is what restrictions does the continuity assumption place on the matrix AR? Well, I've kind of given you the answer there, but let me show you where it comes from. Okay, so first of all, the function h the leading order term is zeta transpose x. Zeta is the gradient, just as we had yesterday. It's all the same. So then by continuity, implies that what it means for the system to be continuous is that for any vector x for which h of x is 0, I have to have FL equals FR. And this is also for all mu. Okay, so I can just write the leading order terms. So to leading order, here implies A plus B mu okay, so this is just leading order, and the B mu's cancel out. AR. Okay, so the two B mu's cancel out. I can move the rearrange and factor out the vector x. So what does this equation mean? Well, it means that every row of this difference is orthogonal to the vector x. So I'll write the ith row of AR minus AL is orthogonal to x. And this is for every row, so for all I from 1 to n. Right. So this is where it gets. Be careful. So it's orthogonal to x. Oh, I see. So orthogonal to x, which means it's orthogonal to the complement, orthogonal complement of zeta. So that's right. The ith row of AR minus AL is orthogonal to the orthogonal complement of zeta. Once we've got to there, then we're good. So therefore, the ith row is a scalar multiple of zeta equals some number ci times zeta. So I can put these numbers into a vector, call it c, and I get exactly that, i.e. AL, C. And is that right? I should have a transpose here, really, because this is a row vector. I want a row vector over there. Yeah, so this difference is it's a column vector times a row vector. So it's an n by n matrix. It's a rank 1 matrix. On the next slide. Not ready for that yet. Okay, so going back again. Here we go. Okay, so once we have that, now we can calculate equilibria. So as before. So we can find whether the left system has a regular equilibrium. So solve for x. And I like to write matrix AL inverse. That's the adjugate divided by determinants. And you get and we want to know, is this equilibrium admissible or virtual? So it's admissible if H of XL is negative. It's virtual if H of XL is positive. So H is zeta transpose times thing, so zeta transpose adjugate. And same as yesterday, the zeta transpose adjugate AL, give that vector a special name, call it rho transpose. Rho transpose. AL. Yep. Rho is zeta transpose. Okay, so in summary, we get some constant times mu. I call this constant alpha L. Okay, so that's all the same as yesterday. So things get different when we look for the right half system. So I've reached my line. So I'll go over here. Can I assume that ends my board of like periodic boundary conditions? Go over here now. So similarly, is the equal adjective D. Okay, I still haven't anything new yet. I've just done the same calculation, but instead of AL, I've got AR. But I seemingly have a different row vector now. So instead of zeta transpose adjugate AL, I've now got zeta transpose adjugate AR. But what I'm going to show you now is that these two vectors are actually the same. Which I think is very nice. So, clean. Should we try a different color? Clean. So what I'm going to show you is that these two row vectors are actually the same. And as we'll see, that the reason that they're the same is because the matrices AR and AL are related by this equation. And I'm going to go through the proof because it uses two mathematical tools that reoccur elsewhere. I think it's helpful for you to see them. Okay. Yeah. Okay, so we're given that AR is AL plus some column vector C times zeta transpose so what I'm going to do first is take the determinant of AR. And there's a nice formula for doing this. Because what I've got the determinant of some matrix plus a rank 1 matrix. And the formula is called the matrix determinant lemma. Matrix determinant. AL bracket. Okay, so that the matrix determinant lemma is exactly this, just this formula. It assumes the matrix AL is invertible, assuming determinant AL. 0. Okay, so I really wanted you to show. I wanted to show you that. Next, I'm going to multiply the whole thing by zeta transpose. Zeta transpose is zeta transpose plus. Okay, so I'm multiplying the whole equation by zeta transpose. So the 1 turns into zeta transpose. I've got a C times zeta transpose. C times zeta transpose is AR minus AL. Slightly longer chalk. What can we do now? Well, we can expand these brackets. So I'll have an AL inverse times AR. I'll also have an AL inverse times AL. And so those will turn into the identity matrix. it would give me a minus zeta transpose, which will cancel with the zeta transpose that's here. So that guy's going to cancel with this one. Equal. Zeta transpose in the so I expanded the brackets here. So I've got an AL inverse times AL, which identity matrix. I have a minus zeta transpose, which is going to cancel with the plus zeta transpose. Okay, so then I'll move the matrix AR onto the right. So determinant zeta transpose adjugate equal zeta transpose AL inverse. Okay, so I multiply both sides by AR inverse, which assumes that AR is invertible, assuming determinant AR is not 0. And that's about it, because you remember that the inverse times the determinant, that equals the adjugate. So the determinant is just a scalar. I can move it to the right of the zeta transpose adjugate. And you get oh, well. I haven't quite completed my proof yet. Okay, there's one more thing I need to do. So my algebra assumes that these two matrices are invertible. But I claim this result holds true for any matrices AL and AR. And so this is the second kind of argument I wanted to mention to you. The point is that both sides of this equation are continuous functions of the entries of the matrices. And if you think in the space of all matrices, matrices are only invertible matrices are dense in the space of all matrices. And so I've got a continuous function, which I've shown it works everywhere except on some extra points. So it's true on a dense set. So because it's continuous, it's true everywhere. So even if one or both of those matrices are not invertible. So what I just said there, dot, dot, dot. And then I can do my box. So essentially, you think on the space of all matrices. I mean, really, I need to think on the space of all matrices AL, like cross all matrices AR, across all vectors zeta. And I prove this equation's true on a dense set. It's continuous, so therefore it's true everywhere. Right, okay, so with all that, I can replace this row vector with row transpose. So H of N equals minus. And what color do I do? Orange. Okay, so I'll call this number alpha R. And so that the signs of alpha L and alpha R, but whether those are positive or negative, that determines which sign of mu that the equilibria are admissible or virtual. So just as in the discontinuous case, we have conceivably 4 different cases. So L. Mu. So yesterday I drew all 4 cases. So let me do the same thing in the continuous scenario. So first of all, let's suppose that they're both positive. So alpha L is positive. For the equilibrium to be admissible, we need this to be negative. Alpha L is positive, so that means we need mu to be negative. So, yeah. So XL is admissible for mu negative. For XR to be admissible, we need this thing to be positive. So if alpha R is positive, we need mu to also be positive. And then I can do all sorts of the other 3 cases. Alpha L is negative, alpha R is positive. So now I've switched the sign of mu for which XL is admissible. So there. Alpha L negative, alpha R negative. Switch both of them. And then lastly, what have I not done? Alpha L is positive. Alpha R is negative. Alpha L is positive, so that one. And this one. Okay, so here are bifurcation diagrams showing that the 2 regular equilibria in these 4 cases. And just as in the discontinuous case, we sort of collect these 2 together. So for the top 2, scenarios, as we vary the value of mu, we just have one equilibrium turns into another one. So that's persistence. And so these happen when alpha L times alpha R is positive. And the bottom 2, you've got 2 equilibria coexisting. They collide and annihilate at the boundary equilibrium bifurcation. That's our non-smooth fold. Non-smooth fold. So you'll see those, that happens when alpha L times alpha R is negative. Okay, so one more calculation to do, and then I'll have an exercise for you. Okay, so we've just seen that what's important is alpha L times alpha R. We want to know if that's positive or negative. So just as we did yesterday in the discontinuous case, we can relate this to the eigenvalues of the matrices, AL and AR. Right, so we've got our formulas for alpha L and alpha R. Sign a rho transpose B squared. Okay, so both the formulas for, here it is, alpha L and alpha R, they both have a minus rho transpose B. So minuses cancel out. You get this thing squared, which is going to be positive. So that doesn't affect the sign. I should have said that we assume that rho transpose B is not zero. This is our assumption. That's our transversality condition for the bifurcation. Okay, so the rho transpose B doesn't do anything here. Instead of dividing by determinants, I can multiply, because I'm just looking at the sign of them. Minus AL. Minus AR. I can bring minus signs in. So by bringing a minus sign in here, I'm multiplying all rows of the matrix by -1. So the determinant changes by -1 to the n. And then I also have a -1 to the n here. -1 to the n times -1 to the n is 1. Doesn't matter if n is odd or even. And then as I mentioned yesterday, the sign of the determinant of minus AL, it's equal to what? It's equal to the number of the number of negative eigenvalues of minus AL. So it's equal to the number of positive eigenvalues of AL. So NL, real, positive. So number of real positive eigenvalues of AL, and NR is for the matrix AR. Okay, so I think this is nice. So what we can do is we can just compute the eigenvalues of AL and AR. Just count the number that are real and positive, and then we can use those numbers to classify the bifurcation as either persistence or non-smooth fault. So, okay, so what I'm going to do now is take a break from talking, and I'll give you a chance to work on exercise 9.1, or you can just take a break. I suppose. Nice. I'll give you a few, like about 5 minutes or so to get started on that, and then I'll go through it quickly on the board. So here's the equations. You're asked to classify the boundary equilibrium bifurcation that the system has at psi equals 0 as either persistence or non-smooth fold. And so you can do it by calculating NL and NR. In here? Yeah, so I did it for both of them. So yeah, you have the determinant of some matrix. I call my matrix X. I just want this, yeah. The determinant of a matrix X, it's the product of the eigenvalues. So it's lambda 1, lambda 2, lambda n. But I have to count algebraic multiplicity, so I actually have n of them. So if I look at this, the sign of this thing, is it negative or positive? Any complex eigenvalues come in complex conjugate pairs. I'm assuming my matrix has real valued entries. If you have two complex conjugate pair of eigenvalues, multiply them together, you get a positive number. And so positive numbers also are positive. So the only way I can get negatives is just with negative real numbers. So that the sign of this thing, it's equal to the number of negative eigenvalues of X. Number of real negative eigens of X. Okay, so let's go through this on the board. The system I've given you is in a slightly different form. We've got absolute values for our switching manifold. So I can rewrite the system in a more familiar sort of piecewise form. So if this thing is negative, I've got a minus x, minus y, minus xi. That should be a plus y. Oh, that's the Jacobian. Minus y. Plus there. I'm confused now. Negative. Oh, that's a minus. So it's still a bit funny because I've got a parameter in my switching condition, whereas all my framework I've just got switching condition being independent of the parameter. But that's not important to answer the question. You just need these two matrices. This is the matrix AL. This one, AR. This matrix traces 1. Determinant is minus 2 plus 1 minus 1. So the determinant is negative. It corresponds to a saddle. Got one positive eigenvalue, one negative eigenvalue. Right, so in particular, we've got one positive eigenvalue. So it's NL is 1. And here we've got traces 3. Determinant is 2 minus 1. 1. It's unstable. Determinant. Tau squared over 4 is 9 over 4. Bigger than 1. Where am I? Trace. Determinant. Trace is 3, so I'm up over there. Right? Yeah. So we remember our tau delta plane from 2D linear systems. We're over here, unstable node. Right, unstable. So that the unstable node has 2 positive eigenvalues. instead of calculating the trace and determinants, you could have also actually calculate the eigenvalues. Okay, so then we put them into our formula, get -1 times +1, -1, and 1, 2 is -1. What does that tell us? So it tells us that alpha L times alpha R is negative, so therefore corresponds to a non-smooth pole. So the saddle on the unstable node will collide and annihilate when xi equals 0. Okay. Any questions on that one? Okay, so next I have another example. So you'll often hear about ocean currents in the news, particularly the Gulf Stream, which is in the Atlantic, keeps Northwest Europe somewhat warm. You often hear about them in the news because ocean currents may be very sensitive to climate change. And so here's a very crude mathematical model, ocean currents in the Atlantic. Y represents the difference in salinity of the ocean at the equator compared to near the poles, and M is some sort of forcing ratio. That the model is piecewise smooth. You've got the absolute value there. It's piecewise smooth because the model assumes that the motion depends only on the magnitude of the circulation, not on the direction of rotation. Okay, so it's just a two-dimensional ODE system. It's continuous, but non-differentiable. So that's sort of system we've been considering. What are the parameters? We've got parameter A, parameter delta naught, and a parameter lambda. So this system has a boundary equilibrium bifurcation at lambda equals 1. You can see if you put lambda equals 1 and try to solve for equilibria, you get y equals 1, and then y equals 1 is where the absolute value is 0. So that's where the absolute value function has its kink. Okay, if you do some analysis, you find that for this range of values of A, so A is between 1 and this number that's bigger than 1, but for values of A in this range, you've got a boundary equilibrium bifurcation. On one side, you've got a stable node. On the other side, you've got an unstable focus. Similar, we had a saddle and an unstable node. You know. So here we've got a stable node, unstable focus. Okay, so let me show you phase portraits. So here I've chosen a value of A that's in that range. So I've chosen delta naught to be 0.01. So then my range is 1 to 1.2. So I choose 1.1 in the middle there. So on one side of the bifurcation we've got our stable node, and then at the bifurcation you've got your boundary equilibrium. Then on the other side of the bifurcation you've got an unstable focus. It turns out that this transition, stable node to unstable focus, you have to have a stable limit cycle being created at the same time. And you can see that here, get small amplitude stable limit cycle. Sorry? What's the... Oh, delta naught. That the value of delta naught is fixed at... Oh, what's the significance? No. I don't remember. It's like a time scale separation parameter, isn't it? Delta naught's small, so make sure that m evolves slowly relative to y. I have to go back reading the paper to give you a more accurate answer. Okay, so let's also choose a value of a that's outside that interval. So now a is a bit bigger. And so now the boundary equilibrium bifurcation goes from a stable node to an unstable node. And so here are the phase portraits. We have a stable node, then we have a boundary equilibrium bifurcation, and now we have our unstable node. And this time you don't get a stable limit cycle created locally. Just ignore the limit cycle there for the moment. The reason you don't get a limit cycle in this case is because both equilibria are nodes. So both equilibria have the eigenvectors. You've got these invariant manifolds on eigenvectors. You can't possibly have a limit cycle because the eigenvectors just get in the way. Nevertheless, you'll notice that there is a limit cycle here. However, it's a large amplitude limit cycle. It occurs due to some global features in the model. So at the model we're looking at, it's not piecewise linear. You've got a quadratic term, a y times a y is y squared. So that the limit cycle is created due to the y squared, like the folding in phase space, like further away. So that's a global feature. It's a global feature. Nevertheless, the limit cycle is created at the boundary equilibrium bifurcation. So you've got this strange kind of gray area between when the bifurcation is local and when it's global. You might think that we could just add more terms into our equations. So I have all these order 2 terms everywhere. If I included the next order, that wouldn't help me. That wouldn't give you the limit cycle. But the limit cycle is far away. I have to include all orders to capture it. Okay, so that's enough on that. Okay. Okay, so next I want to introduce a normal form for boundary equilibrium bifurcations, but now we're in continuous systems. Normal form. Okay, so unlike the normal form I introduced yesterday for discontinuous ones, that normal form I kind of came up with while I was preparing these lectures. This normal form's been around for a long time. I think Mario Di Bernardo, his 2003 paper from memory, it's really the first one that has it. CL plus EN. Okay, so first of all, as yesterday, the scalar x represents the first component of the vector x. I'm finding it's a very icky notation to actually say, but when you're reading it, it's quite manageable. Scalar x, first component of the vector x. Yeah, so we're assuming our switching manifold is where the first component of x is 0. That the matrices are companion matrices, so they're of the same form we had yesterday. And the constant vector is the last standard basis vector En. Yeah. Okay, so in order for this to be a valid normal form, we have to be able to take a sort of generic system and be able to transform it to the normal form. So, so let me write down a generic system and explain how you do the transformation. So we'll assume that for our generic system, we've chosen coordinates nicely so that the switching manifold is just where the first component of the vector x, scalar x, where this equals 0. And again, we're assuming continuity. So AR is equal to AL plus some column vector C. And previously it was the row vector zeta transpose. The zeta is the gradient of the function h. In this case, the gradient is the first coordinate vector, E1. Right. Okay, so how do you transform from here to here? Actually, there's probably some more space at the bottom I could use. Right. Equals. Okay, so we'll write out the characteristic polynomial of AL and L1 plus A L in minus 1 lambda plus A L. Okay, so for any matrix, you could compute this, and you could give names to the coefficients in your characteristic polynomial. So here's what I'm calling them. And then I could use these coefficients to build up a matrix, capital psi. Psi L. So this is the same as yesterday. I keep saying that. So A L1, AL1, and then this one's AL n minus 1. So use those numbers to construct this matrix. And then we also have the same observability matrix that we had yesterday. E1 transpose, E1 transpose, AL. Okay, so multiply those two together, and that's the matrix Q that we're going to use as our similarity transform to get from AL to CL. So in the discontinuous case, we also had a divide by absolute value of C1. We don't need that here. So then CL. Okay, so by doing this construction, when you apply this transformation, AL turns into the desired companion matrix CL. Okay, so what about AR? So this is where things are different to the discontinuous case. The point is that we have to do the same coordinate change on the left and on the right. So I've got to apply the same matrix Q to AR. And hopefully I'll get CR. So I claim Q. Okay, so that's my claim, and it's far from obvious that this is true, but because the matrix Q is constructed using AL. So why should this work for AR? Well, this works because AR is related to AL in this way. And I can prove it to you in a few lines. Q equals Q inverse. Okay, so just substitute in the formula I have for AR, and then I'll expand the brackets. I already know that Q times AL times Q inverse is companion matrix CL. So what about this thing? Okay, so let's think about what the first row of the matrix Q has to be. Well, that the first row of psi is E1 transpose, just 1, 0, 0, 0, 0, 0. Then multiply it with this one. I've also got 1, 0, 0, 0 here. So the first row of Q is just E1 transpose. That's very important because it means when I do my transformation, that the switching manifold doesn't change, so that the X stays as just an X. So then I'll multiply both sides of this equation by Q inverse. I don't have Q anymore. So multiply both sides by Q inverse. And so that's what I can put in here. CL plus Q C Q1 transpose. Good. Right, and the point is that this matrix that I've just written here, that this thing is a companion matrix. So why is this whole thing a companion matrix? Well, I've just got some column vector. It happens to be called Q times C, but it's just some vector times E1 transpose. So that's going to be Q. It's going to be a rank 1 matrix. The first column is QC and the rest is just zeros. So when I add it to CL, all I do is change the first column of CL. I still have ones in my off-diagonal. So this thing remains a companion matrix. It's just a different companion matrix to CL. It's CR. And so CR it's similar to AR by construction. So it has the same eigenvalues and multiplicities as AR. Okay, so that's how the normal form works. I think that's a good place to stop, actually. I think we can leave it there for now. Just have one more lecture tomorrow. How to get from here to here? Just multiply both sides by Q. So I'm assuming Q is invertible. So I do a Q inverse and a Q inverse. Q times Q inverse is the identity matrix. That's there. So how did I get that equation in the first place? Okay, so E1 transpose Q, E1 transpose psi L phi L, just by the definition of Q. So E1 transpose psi, that's the first row of psi. The first row of psi is E1 transpose, so E1 transpose phi. And then the same thing again. The first row of phi, which is E1 transpose. I suppose I left out a step when I was doing it. Thank you. Any other questions? Just here. Right. So hopefully you can see that this matrix, I've got a column vector times E1 transpose. So here's what the matrix looks like. I've got the vector QC in the first column and zeros everywhere else. So when I add it to CL, the CL is I've got my A's. I've got 1. So when I add these two things together, I just get some thing in the first column, and then I've got just my 1s here. So I conclude that this thing is some sort of companion matrix, and it has to be similar to AR. You do the same calculation for the border question normal form. Actually. Okay. Well, thank you.